Great. Good afternoon, everyone. Welcome back to our afternoon programming. I have the pleasure of introducing our afternoon session focused on the remediation of PFAS involving techniques, policies, and cost benefits. This is a rebroadcast of a session that was filmed last night, recorded last night by some colleagues in Australia, chaired by Dr. Jochen Mueller of the Queensland Alliance for Environmental Health Sciences. So without further ado, please tune in. Over the course of this, you can drop some questions in the Whova chat, and we'll have a live discussion at the end of this session led by Dr. Mark Striner, focused on remediation and non-target analysis of PFAS. Thanks so much.
So thanks everybody for coming to this remediation session. It's really an experiment for us too, because it's our first one doing this over Whova and as well as Zoom. This is Sarit, Dr. Sarit Casason, who is responsible for all the bugger ups, and I'm responsible for all the things that's going to work out really well. Anyway, let me first start with acknowledging the traditional owners of the land on which we are sitting. And also our keynote speakers are from Melbourne and from Sydney. So really we cover the whole of Australia. So we would really like to acknowledge the traditional owner of whole of Australia and allowing us to be on their land and their ancestors in the past. The future. So this is a session that came about when Rainer asked me whether we would like to do an Australian leg of this, of FLUOROS 21. And initially he asked us whether we would do something about environmental levels. And that, when I thought about it, I thought that was a bit boring. And Australia has particularly spearheaded a lot of work in the remediation sector. And PFAS has really been a big thing in terms of moving forward and trying to find solutions. And so I proposed to Rainer a remediation session, and he was immediately agreeable to that. And so this also links us very much to various SRI grants. And it's our great pleasure to then select a number of people who work in this remediation space. And since we are really in Australian, Asian, and more or less at the start of the European time zone, we decided we invite local speakers, some local keynote speakers, and speakers from Europe, and one speaker from Europe. We're now hearing Carl Bowles as our next keynote.
Hello, and thank you for this opportunity to talk to you about PFAS remediation, in this case focusing on what's happening in Australia, and trying to answer the questions what's possible right now and what's practicable. Pointing out I'm a consultant with RPS, but I'm also contracted to Australian Department of Defence within their PFAS management program. This presentation represents my thoughts as a consultant, not directly representing Defence. Thank you to some of my colleagues who do work in that Defence PFAS program. Also Eric Cooper, who is a colleague from North America, and Ben Hunter, who helped with one of the larger case studies that I've got here in the slides there. So it wouldn't be a consultant's presentation without a disclaimer, just pointing out that I've mentioned quite a few products and companies in here. I'm not endorsing any of those, it's merely for information. So I'd like to start off by talking about PFAS treatment technologies we're currently using in Australia with a focus on groundwater and soil, move through to then to what technologies are emerging in the R&D space, and then what can be achieved. And this is particularly important, is asking the questions about how do we set remediation objectives for the particular problems that PFAS presents. So let's start with groundwater. And straight off the bat, we're very good at pulling PFAS out of water. The problem we have is that restoring an extended aquifer is generally not practicable, whether that's for PFAS or whether that's for many other contaminants. But there still may be sensible reasons for pump and treat. So, for example, if you have a concentrated contamination at a source zone, it may be sensible to pump and treat to get PFAS out of the ground, so a grab for mass. You may be trying to address a specific risk, so there you might be treating to below a particular threshold value that you decided as your objective there. Another objective could be hydraulic containment. So if you have a contaminated part of an aquifer and you want to stop that from moving to another area where it's going to impact on receptors, then hydraulic containment, stopping that water, contaminated water from getting there, could be a useful objective. And whatever your objective is, that's going to inform your choice of technology. So for water in Australia, we currently have many commercial options, various companies. They're dominated by concentrating onto a solid, so either by ion exchange or activated carbon, or not just activated carbon. There are a variety of solvents that can be used, and so I've listed a range of other proprietary solvents here that are also being used here. And there's also quite a different approach called foam fractionation. And what this does is it relies on the surfactant property of PFAS, uses that to an advantage. So if you bubble water, or in one case ozone, through your water or your wastewater, you can form a foam that will take the PFAS with it, so strip the PFAS from solution. This has got growing popularity, and in fact, I believe OPEC Systems has water treatment plants using foam fractionation now in several countries around the world. There's also membrane separation, such as reverse osmosis and nanofiltration. These work. They do pull PFAS out of water, no question. But what I've observed here is that they tend to be used where the primary goal is to pull out other contaminants. When it's a standalone PFAS solution, tend not to be used so much. There are fixed and mobile rigs for on-site treatment of groundwater, and there's also off-site facilities if you want to truck your water away and you don't necessarily have the economics to set up a specific on-site treatment solution. Here's a case study. So this is from Australian Defence, the Army Aviation Centre at Oakey. So if you look on the left, that red and black box, that's the Army base. There's a number of source areas on site, and there's an extensive plume of primarily PFOS and hexane sulfonate contamination that spreads for a large distance, and a lot of it underneath the town of Oakey, which has about 2,000 people. The concentrations in that plume, depending where you look, tens to hundreds of micrograms per litre. Defence has set up 2 treatment plants there. One is operated by ECT2, it's an anion exchange plant. The other one is run by OPEC Systems, and it's a foam fractionation plant like I just talked about. When that foam fractionation plant was first set up, it was originally a trial. It's now progressed to a normal contractual procurement, and it's an example, a good success story of a developing technology that's moved through to being used on a commercial basis. The influence there for treatment, currently approximately 5 to 10 micrograms per litre, and both of these plants are required to treat below the Australian drinking water standards, which are sub-micrograms per litre for PFOS, hexane sulfonate, and PFOA. Both plants routinely achieve results of below limited reporting for these 3 PFAS, so less than 0.01 micrograms per litre. Both of the plants are using treatment trains. In the case of the anion exchange, you want to protect your expensive resins from fouling, so have some upfront steps. In the case of the foam fractionation, if you need to achieve low single-digit nanogram per litre treatment targets for short-chain PFAS, such as PFBA, you might need some polishing on there, so such as anion exchange or activated carbon or other amendments. The fate of the treated water for these 2 plants is different. In the case of ECT2, it's reinjection to aquifer. In case of OPEC Systems, it's irrigation of dry bushland. That's not related to the technology. That was just simply for practical reasons at the time that the 2 plants were set up. Usefully, both plants, projects on base can apply to use the treated water for their projects, for example, dust suppression on construction projects. And so there can be a resource recovery element to this as well, which brings extra value. So moving from groundwater, what about surface water? As I said before, we've got to point PFAS from water, but there are very pronounced logistical constraints for surface water. And really that centres around, can you hold water for long enough to actually have some kind of treatment on a reasonable timescale? And particularly in Australia, north of Australia, where we have tropical systems, but other parts of Australia, very high rainfall, it's very difficult simply to have that water storage for significant time to actually achieve this. Again, Australian Defence has got a trial going through a company called Synergy at Lake Cochrane at Williamtown. So they're trying a range of approaches through gabions, bags, weir boxes, etc., using activated carbon to see, look into these passive solutions. So moving from water to soil, what can I do with PFAS contaminated soil? Our options here are more limited, and our remedial approach is very, very much influenced by the PFAS distribution on sites. And what we very much typically see is that we see small areas with high concentrations of PFAS, so above 10 milligrams per kilogram, and extensive areas of soil with lower concentration PFAS. This is just another figure from an investigation report which shows that hotspot distribution is not just laterally, but also it's vertically, where we tend to see the highest concentrations of PFAS around the surface of the soils. But still, lower concentration impacts more extensively. So let's think about the high concentration source zones. First, obviously, in some places there are off-site solutions. So landfills, or in some cases a geological repository. This can be seen as good because the problem goes away for the polluter, but there can be ongoing management for the landfill operator. And depending on how the regulation is in your jurisdiction, there could be ongoing liability for the government as well. In Australia, we're fortunate that we do have some centralised thermal facilities that are specifically licensed for receiving PFAS impacted material. These plants must achieve conditions for PFAS degradation. In other words, they're not simply desorption technologies. They have to be engineered to control the hydrofluoric acid that's produced as part of the destruction and handle other off gases. It's important that projects who might want to be using these facilities consider facility capacity, what's the throughput for these, and so they are particularly amenable to these high concentration source zones as opposed to the low concentration extended areas. In terms of on-site solutions, we have a few things that we can use at the moment. And these really centre around controlling PFAS pathways to receptors, in other words, PFAS mobility. So you can use engineered stockpiles. Typically, these are not used so much because they're not a set and forget. They cost a fair bit to actually set up in the first place. And then there's ongoing management, so controlling leachate from the stockpiles, etc. So not used as much. Capping is something that is achieving quite a lot of popularity in Australia. And so this is stopping rainfall from accessing the ground and leaching the PFAS out of the soil into groundwater, into surface water. And this can be as simple as producing a car park in a sensible location and just breaking that pathway of water getting to the soil. There's also soil stabilisation, and I'm going to talk about that in a case study later. So let's move to the areas of low concentrations of PFAS in soil. What we're finding is that where we have large areas of soil, even though the concentrations of PFAS are low, so circa about 1 milligram per kilogram, these soils can still contribute a significant flux of PFAS mass from sites, particularly in surface water. And so even though the concentrations are relatively low, they still need to be managed. Removing all of this soil is not economical, it's not environmentally sustainable, there are transportation costs and other resources for doing it, and the value of the soils are lost to whether it's landfill or thermal destruction, the value of those soils are lost. And so simply removing that soil is not a great solution. So looking to on-site solutions is great. Again, engineered stockpiles can be used, but with the same problems that we mentioned on the last, and also if you have a large amount of soil, there's very, very often space limitations. You are very unlikely to have the space on site to stockpile large volumes of soil. So stabilisation is one that we're looking to, and again, I'll bring that up in a minute. In terms of the overall strategy, just wanted to make the point that your site remediation strategy is almost always going to include a range of approaches and technologies. It's not going to be a single solution. And also just pointing out that some of these solutions currently used focusing on minimising movement of PFAS, such as capping or stabilisation, while they're very effective at reducing risk in themselves, they may also have an additional benefit that over time, when there are more permanent solutions, so destructive methods, for example, that using these approaches may give us time until some of those approaches are developed. So, as I said, in situ destructive methods as they're developed, and perhaps passive or low energy technologies that will also be more economically valuable. So that brings us to emerging technologies, and we'll just quickly have a look at some examples of some R&D in Australia and a case study. So the Australian Research Council is a funding body that provides funding to research in Australia, often with linkage projects between universities and industry. They have funded 12 projects for around about $11 million under a special research initiative for PFAS. And these projects are really primarily about remediation technologies. Of the 12 projects, the majority of them are centred around technologies for destroying PFAS. There's a couple of projects that are around improved ways to remove PFAS from various media. A lot of the destruction technologies are focused on thermal approaches, whether it's conventional thermal or whether it's other thermal approaches such as pyrolysis replacement. The media target are quite diverse, and importantly, the vast majority of the projects are centred around ex situ treatment solutions. So, in other words, get the soil out of the ground, do something with it, get the water out of the ground, do something with it. Only one project is centred on an in situ approach. A quick snapshot here of some other research in Australia, and by no means is this meant to be comprehensive. This is just a few things that are going on. And so, for example, in the soil immobilisation space, there are companies doing quite a bit of research into technologies for soil immobilisation. Similarly, concrete immobilisation strategies. Destructive technologies also, people looking into various things such as microwave technologies, electrochemistry, and also point of use treatment systems for drinking water, and the list could go on. And what I do want to highlight here is PFAS immobilisation or stabilisation. Now, fairly recently, we've made scientific advances which have given us a much better understanding of PFAS mobility, how it acts in soils, and its transport from soils. And what this research has done is it's given us some confidence to implement solutions that minimise risks by minimising PFAS movement. So rather than removing the PFAS or the soil entirely, these stabilisation type approaches. And stabilisation, it's been used extensively for a range of contaminants, and it's now emerging as an effective solution. PFAS, you can use activated carbon, but just like water treatment, there are various proprietary products which are also successful, as far as we can see, at being able to stabilise PFAS in soils. So the case study here centres around the Air Force Base at Richmond. This one's using powdered activated carbon as an amendment. And this is a full-scale trial that's undergoing, but it was backed by a lot of work leading up to that trial. And so research funded by Defence from the University of Adelaide and CSIRO, including studies to simulate what are the long-term effectiveness of these solutions. Also some pilot scale field trials from Defence and their consultants. And then leading up to this particular case study at RAF Richmond, as I said, where they have treated 4,700 cubic metres of soil in batches. The PFAS there is primarily PFOS and hexane sulfonate with concentrations in the range of 5 to 50 milligrams per kilogram. Validation at the moment, primarily using Australian standard leach procedure, and this is a lab procedure similar to the US EPA TCLP procedure, if you're familiar with that. And thank you to Steve Korish and Ben Hunter for the following slides for this case study. So here we have a fairly shallow hole in the ground, and that's because the investigations revealed the PFAS was very much concentrated in the top levels of the soil, which is something we see quite frequently at sites in Australia. So dig out soil, put in a GCL, a clay liner. And initially the project used a pug mill, which is just a standard technology for mixing soils at scale. And there were problems observed here trying to mix the activated carbon in with the clay soils of this site. So the project pivoted and tried a different approach, which was in-ground mixing using a digger. And what they found was after about 30 minutes of mixing, they actually achieved a good level of mixing of the activated carbon through the soil. So a good outcome. So then it's a fairly simple approach, put the amended soil back into the ground, compact it, put in swale drains as necessary, turf over the top. So do we have data to show how it's working? We have some preliminary data, and there will be more data that comes over time. So the leachate concentrations, the lab leachate concentrations prior to stabilisation in the tens to hundreds of micrograms per litre, dropping to single digit or below micrograms per litre post-stabilisation. The average percentage reduction in the leachability, 99.8%. This is a fantastic outcome for this work. Be able to be used for other uses. Important to note here, there will be further testing and there will be environmental monitoring over time to show that this is an enduring solution. So now moving away from technologies and onto the question of objectives. So talking about site remediation objectives. And here I'm not talking about what your treatment targets for destruction might be or what your targets for release or replacement of treated materials back into the environment might be. Very much asking the question of setting objectives, what's possible, what's practicable. And of course, this is very important for a raft of reasons. Your objectives are going to influence what's needed from the technologies that will influence your choice of technologies. What you can achieve, and very importantly, what you can't achieve, can be very difficult to communicate to other stakeholders, including communities. And so it's very important that you understand your objectives and are very clear on that so that you can make that communication as best as possible. There's also the issue of what it's going to cost to do these things. And so what is a reasonable, attainable outcome? And that's part of the objective setting as well. Now, PFAS can throw some additional complications into this. And so often contaminated sites are large and complex, multiple source areas, extensive areas of contaminated soil, as we've discussed, large diffuse contaminated aquifers. Something else we've learned that surface water pathways are often much more important than many other contaminants compared to transiting groundwater. That has to be considered. And sometimes unwittingly, the extent of contamination might have been exacerbated in the past by practices such as irrigation with recycled wastewater. There are some organisations who have many small sites, so typically fire services organisations, and so they have complications in terms of how they prioritise their resources in terms of dealing with those many small sites. Also, many sites are public owned, so publicly owned airports, defence bases, fire services, etc. And that means that the costs from remediation are going to be an impost on taxpayers. So this comes out of our pockets to some degree. So we need to be very careful about how we set objectives and what we're trying to achieve. And there are various ways we can go about doing this, various paradigms. The simplest would be a hazard-based approach. And so you might make the argument that these are synthetic chemicals, they're not supposed to be in the environment, so we're just going to get all trace of those chemicals out of the environment. But more often in the contaminated land space, we have a risk-based approach. So we identify thresholds that we consider acceptable, and we'll do appropriate work to make sure the concentrations that are achieved from remediation are below those. And that's also consistent with typical water frameworks, water quality guidelines, etc. And there's an extension of risk-based frameworks, which has various names, but for the here we'll call it so far as reasonably practicable, or SPART. It's essentially risk-based, but it can also make allowance for other parameters, other factors. So for example, what's achievable based on the technologies that are at hand? What's the environmental sustainability of the overall solution? Can also consider proportionality between the costs to achieve mitigating the risks and the risks themselves. Now, taking this approach does not mean that you can ignore risks. It's important at the end that all risks are managed, but what it may mean is that there may need to be other controls apart from remediation in order to address some risks, such as administrative controls. The concept of reasonably practicable is not new to Australian legislation. It's been in our Work Health and Safety Act, specifically mentioned, for example. More specifically for contaminated land, Victorian EPA has included it in their environmental legislation. They talk about reasonably practicable, meaning that you must put in proportionate controls to mitigate or minimise harm. So again, it brings up this concept of what is proportionate. Moving to an example here, again from Australian Defence, PFAS management program. Defence conducts thorough investigations to ensure that the risks are identified, and it summarises these risks in what they call PFAS management area plans. And these are documents that have been designed to capture the information from these complex sites with multiple source areas so that those risks can be prioritised and you can look at what you need to focus your resources on first. So currently that's involving targeting PFAS movement from source areas and at various sites using a range of remediation solutions. And these are the solutions that we've talked about in this talk so far. Very, very importantly, there is monitoring to understand the reduction of PFAS mass flux leaving the site, so you can know whether your remediation has done what you want it to do. And then again, importantly, you need to iterate. You need to go back to your PMAPs, feed in the monitoring data, look at your new level of risk and look at what the next steps need to be for any further management. Now, of course, in any program like this, and particularly when you're talking about things like proportionate and so far as reasonably practicable, different people are going to have different opinions on what that means. And so in Australia, we're very fortunate that in many states we have a program of environmental auditors who are independent people accredited by EPAs in order to provide independent assurance that proportionate response has been achieved. And so where possible, auditors are used. In some cases, they're technical advisors. So not with a formal auditing role, but still the intention is to provide this assurance that a proportionate response has been achieved. On top of that, Defence is also investing in research to try and expand the options for responding. So not just about what we can achieve now, but what can be achieved in the future. And considering that is an important part of this so far as reasonably practical approach. For some jurisdictions, moving regulatory targets add to the complexity as well, and this can factor into objective setting. In Australia, we're fortunate that we've had a PFAS National Environmental Management Plan for a few years now. That's helped provide some consistency. In some places, there's still a lot of action in that space. Just an example here in the US for drinking water standards alone, there's a raft of different levels of guidance or enforceable or non-enforceable criteria, depending on whether you're looking at the federal level or whether it's at individual states. And of course, there are a whole raft of stakeholders involved who are aware of PFAS concerns and they want to mitigate their business risks. So as well as the environmental risks, there's the business risks involved as well for a raft of stakeholders. So this presents extra challenges. So summarising all of this, as I mentioned at the beginning, we're quite good at doing PFAS from water, but restoring a large diffuse aquifer is something that will remain impracticable. There are good reasons for treating groundwater, for example, but it's very important that we understand what our objectives are for doing that. For soils, we have far fewer options, particularly we have fewer in situ solutions. And soil stabilisation is emerging as one with extremely good promise in that space. The solutions we do have primarily involve breaking PFAS transport pathways. So that could be stabilisation, capping, etc. Off-site solutions sometimes exist, but they're very much limited by local availability. In some cases, there aren't landfills that can take PFAS contaminated material or thermal facilities that are licensed. In some cases, there's also complications with community relations who may not want these materials coming into their area. There are many technologies in development for destroying PFAS, which is quite promising. And finally, in terms of objective setting, this very important issue, remediating large complex sites or prioritising many small sites really suggests that an approach such as so far as reasonably practicable can be implementable for achieving proportionate responses for PFAS contamination. So it's part of an ongoing dialogue that at the moment we're having in Australia, and it'll be interesting to see how different jurisdictions around the world address the issue of objective setting for these types of sites. So thank you very much for listening. Again, it's been a pleasure to have this opportunity, and I look forward to the opportunity to take some questions later on. Thank you.
Hi. Hi, everybody. I am now not sure whether Lutz is there. Just looking through. I think Lutz is not live there. And if Lutz is not live there, we have to probably go and listen to his pre-recorded presentation, which had some issues with it. Sorry. Sorry, quickly, I'm a bit unprepared for this one. No panic. Oh, by the way, if you're, please type your questions into the Zoom box.
Hello, everyone. My name is Lutz Ahrens, working at the Department of Aquatic Science.
Share screen. Okay.
Hello, everyone. My name is Lutz Ahrens, working at the Department of Aquatic Sciences and Assessment at SLU Uppsala, Sweden. Today, I will talk about PFAS treatment technologies for drinking. And for this, we move now to Sweden. Here, you see the map, and more specifically, research was performed in Uppsala. And here in Uppsala, there has been a study in 2012 from Anders Grill and co-workers finding exponentially increasing concentration of several PFAS, such as PFAS and PXRS, in blood serum from pregnant women. And this was unfortunately discovered too late, since the population was already exposed at this time. And the PFAS contamination of the drinking water was responsible for the elevated serum levels in mother and child. What are these hair and follicular substances? They're used in many different consumer products and industrial products, such as Teflon, Gore-Tex jackets, personal care products, electronics, paper products, like aqueous firefighting foams, and many, many more applications. And from their usage, can be released in the environment. So when you look at the circulation of PFAS in the environment, starting from the industry where they are produced, for example, aqueous firefighting foam contains high levels of PFAS, but also the waste from the industry or from the usage of products can end up in wastewater treatment plants and landfills, from where it can go further, be released into the environment and can reach the food, such as the drinking water, and expose. And there are many other consumer products which can be released into the environment and circulate. And today I will focus on the contamination of drinking water and how we can remove PFAS in drinking water before it reaches the human. Where does our drinking water come from? So here's shown an overview about the drinking water sources in Sweden. So around 50% comes from surface water, 25% groundwater, and 25% artificial infiltration. And based on the EFSA report, drinking water is our main food source. Everyone of us takes approximately 2 to 2.5 liters drinking water. Okay. Let's move to a conventional drinking water treatment plant, which we have investigated. And so the drinking water plant takes the raw water from the lake. We have conventional treatment such as precipitation using aluminum sulfate, we have a sand filter, we have granulate activated carbon. They have also disinfection of the drinking water. We have looked for the PFAS concentrations in these different treatment steps. On the y-axis, you find the PFAS concentration nanogram per liter, and the x-axis, the different water types, and also from the different seasons. And here we can see the raw water concentration by between 8 and 20 nanogram per liter, some PFAS. And when we look at the sand filter, there are basically no changes, concentration approximately the same. We see a small reduction after the granulated carbon filter, and again, no changes in the drinking water. Overall, we see a reduction of about 10% in this conventional drinking water treatment plant as an example. This shows that conventional treatment plants are not able to remove PFAS. So in general, what's going into the drinking water plant coming out of it. However, there have been implemented guideline values for PFAS in different countries. So here's shown an example of which guideline values have been implemented PFAS in drinking water in Sweden. And since 2013, we have the guideline value for the sum of 7 PFAS, which cannot exceed 90 nanograms. And in 2016, the National Food Agencies has added more PFAS to the list. So since then, we have 11 PFAS with a drinking water limit of 90 nanograms per liter, the sum of these 11 PFAS. And in December last year, the European Parliament has decided updated the drinking water guidelines. So there have included the sum of 20 PFAS should not exceed 100 nanograms per liter, and the total organic fluoride should not exceed 500 nanograms. However, this has not been implemented yet in the member states, so they have 2 years' time to implement this new drinking water guideline on national regulations. And there will be probably more regulations in the future. So right now, we have still the drinking water guideline value of the sum of 11 is a limit of 90 per liter here in Sweden. And if we look how PFAS can reach drinking water source area, often fire training sites is a source for PFAS, and doing these specialist training exercises, PFAS can reach the groundwater and also contaminate drinking water reservoir, contaminate our drinking. This exactly happened here in Uppsala, in Sweden. Here we see the groundwater flow of Uppsala. So we have from the north to the south a strong groundwater pathway, which has been used since long time as a drinking water source. And in black, you see the drinking water plants. And here you see the two main drinking water plants in Uppsala. We have one in the north and one in the south. However, the Swedish Defense Department have used PFAS-containing firefighting foam over a long time, over decades. And these PFAS have reached groundwater and contaminated drinking water source levels. And as you can see on the map, the drinking water plant in the north was not affected or very little affected, but the drinking water plant in the south we see high affection with high contamination of drinking water sourcing. And when we look at the southern drinking water plant, the levels are above 150 nanogram per liter for the sum of 11 PFASs. The concentration is still increasing since the plume has not reached fully the southern drinking water wells. And it's exceeding the current drinking water guideline of 19 liters. So yeah, what we need advanced treatment technologies to remove these PFASs from drinking water sources. So what kind of options do we have? One option for drinking water treatment are absorption treatment, such as activated carbon, anion exchange, but also novel materials like functional paint materials. Second option is to separate techniques such as membrane, like nanofiltration or reverse osmosis, membrane isolation, and surface active foam fractionation. And then there are also degradation treatment techniques, such as electrochemical treatment, photocatalytic treatment, and so on. Now I will go step by step through these different treatment options, how feasible they are, and if they're already applied. Let's start with absorption treatment techniques. As an example, activated carbon and anion exchange. There have been many studies on these absorbents for the removal of PFASs. And PFAS can differently interact with the solvents. There can be electrostatic interactions, where the ionizable PFASs can absorb to positively charged surfaces. Or if there are 2+ ions, they can also be attracted to the solvent. But they can be also repulsion. So if there's negatively charged areas, the ionizable PFASs, which are typically negatively charged, can be repulsed. Another option is the hydrophobic interaction. So the longer the chain length, the more dominant are the hydrophobic interaction, where the fully fluorinated tail can interact with, for example, natural organic matter. And there can be also PFAS aggregation of micelles. There are many different types shown for the removal of PFAS. We have done a pilot study where we have tested activated carbon and anion exchange. So we have spiked the water, pumped the water through activated carbon and anion exchange colors over 207 days, and the contact time was 5 to 6 minutes. And here are shown the results only for the granulated activated carbon. We see on the y-axis is removal efficiency, so 100% means everything removed, 0% means nothing is removed. And on the x-axis, we see the bed volume from 0 to 50,000, and also a time scale, so 200, representing 270 days. What we can see is that the different PFASs, different function groups and different chain lengths behave very differently in these activated carbon colors over time. So we see on the top, after 270 days, still very high removal of these tetra pH, the C13 perfluoride fuel chain length. We see even an increase in the end where we have hypersize mice cell formation or aggregation of PFASs. For PFOS, we still see around 60% removal after 217 days. For P4A, around 30%. And here for the shortest chain PFASs we analyzed in the study, P3A, we see even a negative removal, which means after around 22,000 bed volumes, we see a desorption of the short chain P and P3A and a release into the water. We see a negative removal efficiency. This was for both, for the granulated active carbon and anion exchange disorders. So here we can already conclude that the shorter the chain length, the more difficult it is to remove these PFASs using an activated carbon or anion exchange. So then we have tested separation techniques also. Here an example. We have tested nanofiltration with a molecular cut of 207 Dalton. And here we saw very high removal efficiency of over 98% of different PFASs. However, what do we do with the reject water? We have around 15% reject water from the membrane, which we cannot release into the environment. It contains high levels of PFASs. So we combine the membrane with the granulated active carbon and anion exchange column to see if we can improve the overall removal efficiency. So here we see the removal of PFASs in milligram per liter absorption material, which was anion exchange granulated active carbon. We look only for the removal for raw water. Here we can see the total amount of PFASs removed per liter absorption material. We see quite similar results for the anion exchange, which is in orange, and for the granulated active carbon, which is in general quite good. However, if we look at the reject water, which is around 5 times higher levels of PFASs, we see that the removal efficiency was higher in total per normalized liter absorption material. So for the granulated active carbon, we see an improvement of 2.6-fold, and for the anion exchange, over 4-fold better removal efficiency per milligram removed per liter absorption. So here we can see that the combination of nanofiltration with this absorption improves the overall removal efficiency of PFAS. Coming to another example of the separation technique, surface active foam fractionation. This is quite a new technology for PFASs. So how does it work? So it's very simple technology. So you inject air at the bottom of the column, and since PFASs are surfactants, they accumulated in the bubbles and also concentrated in the foam on the top of the column. Hereby we can easily remove the foam and remove the PFASs from the water. And we have tested it for different water types with different levels of PFASs, and also in the various different conditions. We see very, very consistent removal efficiency, even if we have different water types, different conditions. We have already around 10 minutes, we have equilibrated conditions with this about 85% removal efficiency for the sum PFAS. So it was a very efficient treatment technique. However, the removal efficiency for the shorter chain PFASs were in general much lower than at the moment. However, what do we do with the foam? It's a very high concentrate foam with high levels of PFAS. So what to do with this? There we tested a number of degradation technologies. For example, electrochemical oxidation. We use it by high energy to break down PFASs. And there has been a study looking at the degradation of PFASs, become a shorter chain PFAS, and up to a mineralization. However, we have to be careful with this, that we don't create, for example, transformation. Another option for the degradation of PFAS is sonochemical degradation, where the transducer is creating bubbles in the PFAS, since their surfactants are accumulated in bubbles. And when the bubbles are bursting, a high energy will be released, and this until the mineralization of PFAS. However, you can also create low molecular PFAS molecules. Just to give you an overview about the different PFAS options for drinking water based on the stage of development on the y-axis and range of activity on the x-axis. We can conclude based on the studies that activated carbon anion exchange are good treatment techniques for removal of PFAS. However, they get saturated over time and they have a lower removal efficiency, especially for shorter treatments. Another treatment option, which is very high stage of development, are membranes, nanofiltration works of mosaic, which can be already used in full scale and very efficient and removal of PFAS. However, we also need to take care of the reject water. Other treatment techniques are quite high in the development of hemolysis, foam fractionation. There are a large number of other treatment techniques which are right now more experimental scale and has not been applied in full scale in more treatment techniques. And many of them are more degradation of destruction. Let's move on to a case study for the removal of PFAS in full-scale drinking water treatment plant. Here you can see this drinking water plant in Uppsala receives their water from 2 wells. As you have heard before, the groundwater is contaminated with PFAS with the typical treatment steps with aeration, reactor, pH adjustment, sample filter, and then they have granulated activated carbons, so 10 in total, disinfection, and then it goes out to the population, which serves around 80,000. And here we look at the removal efficiency from carbon filters. We look at the influence of fluoride, and we look at the full-scale removal efficiency. Starting with the removal efficiency of the gap filters. Here we compare in full scale 2 different types of activated carbon. It was the FLUOROS 400 and the FLUOROS 2000. And on the y-axis, you can see the removal efficiency in percentage. Again, 100% means everything is removed. And on the x-axis, the number of bed volume treated from 0 to around 35,000 from FLUOROS and from 0 to 28,000 from FLUOROS. And if we compare the removal efficiency for the Hexa-S, we see that after around 80,000 bed volumes from FLUOROS, it's still 90% removal. But when we look at FLUOROS, it's already after 15,000 bed volumes with 90% removal. But in this case, the FLUOROS showed better removal efficiency in comparison to FLUOROS. This is what they're using also right now. So they have started with FLUOROS in the case and now with FLUOROS in the full scale treatment. When we look at the influence of fluoride or the granulate activated carbon on PFAS removal efficiency, here we compare the relatively new filter, which was 85 days in operation with 7,200 bed volume, and compared it with an old DAC filter with 275 days operation and around 22,000 bed volumes treated. And again, on the y-axis, we see the removal efficiency, and on the x-axis, we see the fluoride. And we tried the fluoride under full-scale conditions. What we could see that in general, the old filter was more affected by changing also the flow rate compared to the new filter. So when we increase the flow rate, we decrease the removal efficiency. And this we actually using now in full scale. From the beginning, the filter, the flow rate for the filter is 39 liter per second. And here you can see the removal efficiency for the different PFASs over time. It's decreasing. And in the end of the life, it's one of the active carbon filter, they lower the flow rate around 18 liter per second. Hereby they extend the lifetime of the activated carbon filter. Hereby they save actually cost. So by adapting the flow rate strategy, this company, drinking water supply of solar and use the activated carbon filter for longer time and save cost also. In the end, I would like to show the overall removal efficiency of PFASs. Here we see in the beginning the two wells. So well 1 was much higher contaminated than well number 2. Here we see the sum concentration nanogram per liter. Then well 1 and 2 were mixed. After the reactor, almost the same concentration. After the sample, nothing of the PFAS is removed. And then we see the PFAS concentration in the different GAC filters. And you can see that removal efficiency depending on the bed volume treatment. So in general, the new GAC filter has a better removal efficiency than the old. But for all GAC filters, the PFAS levels are way below the drinking water guideline of 90 nanogram per liter for the sum of lead PFAS. And here, the advisor remove the PFAS efficiently. This is bad. What are the future challenges? The future challenge is that there are more and more strict drinking water guidelines implemented. The next step would implement soon in national guidelines is the new drinking water guideline from the EU. It's 100 nanogram per liter, and also for the total organic fluorine of 500 nanogram per liter. So the drinking water producers have constantly adapted their treatment strategies to be able to reach these drinking water guidelines. And more PFAS is discovered. We know it's a large group of chemicals, probably over 6,000 different chemicals. The more strict drinking water guidelines will be implemented, and the drinking water producers have to solve the problem of the PFAS contamination and to produce safe drinking. About our future work, what we're planning right now, we received a large grant and we're planning to combine different treatment options for the removal of PFAS. And hereby, we are treating PFAS contaminated groundwater, which has around 8 nanometer. And from this nanofiltration membrane, it's very efficient in removing PFAS. So it's producing around 2 nanogram per liter, which is safe for drinking water consumption. And then for the membrane concentrate, around 1,000 to 4,000 nanogram per liter, we will planning to test different strategies, including surface active foam fractionation, electrochemical oxidation, and also ion exchange. Thank you very much for your attention. If you have any questions, please feel free to contact me.
Okay, everybody. So we had the 3 keynotes, great keynotes, complementary, different perspectives. Now we propose here that we have a 15 minutes break, 20 minutes break, come back around 4 o'clock our time. And then we do question and answer. I hope Lutz will be arriving, hopefully. I know it's a little bit early in Sweden. And then after that, we go through a number of posters for those who are interested to stay on. So we do posters that have some pre-recordings, which is about a handful. Okay, so let's have a break for 15, 20 minutes, back at 4 o'clock Brisbane time, 5 o'clock in southern states, and just add 20 minutes to wherever you are. See you then.
Very conveniently for us, we are also going to reflect that break here in person and in our current programming. We'll take a 20-minute break from programming and resume the recorded session with that panel discussion and the poster session at 4 p.m. Eastern Standard Time. In-person participants, also a heads up that there are drink tickets available. There's a drink ticket for you to pick up at the registration desk for a small reception later this afternoon. Don't forget to also stick around. We have our live panel discussion associated with this session, as well as the non-target session from yesterday at 6 p.m. tonight. So we'll see you soon. Hi, folks. We are coming to the end of that 20-minute break. It's about 4 p.m. Eastern Standard Time, so we'll resume that pre-recorded panel discussion and poster session here in just a minute. We will also have our live session at 6 p.m. Eastern Standard Time, and we'll be joined by colleagues from Australia and Beijing in that session. Enjoy.
Okay, I think it's, if the bandwidth allows us, maybe we can all show face. How would that be? Haha. Robert? Yes, Jen, Carl. I don't think Lutz is available. I hope he is all right. I hope it was just some miscommunication issue. So, questions. Let me start with a question to all of the speakers, including Lutz, who is not there. It seems to be all about AFFF, although my understanding is that AFFF is only 5% of the PFAS. So is that because we don't care about PFAS that come from other sources, or is it because it's not worth to remediate? Carl, unmute yourself, so speak freely.
So that's a reasonable starting position for Australia. So in Australia, where we don't have PFAS manufacture, we have PFAS use. Now, we do have uses apart from AFFF, so we do put PFAS into protecting carpets and couches and clothes and everything else. But the route to environment for those has not been as significant as taking PFAS in a plastic drum, essentially diluting it water and spraying it out on the ground, and then doing that every week for 30 years. So route to environment is a really, really key issue here. So if you go over to US or China or Europe, where they have PFAS manufacturing sectors, if you happen to live close to those manufacturing facilities, you're going to be exposed in a whole lot of different ways. I guess also maybe part of that is in Australia, our human health guidance value is at a level that exposures from all the various other things, the household dust and so on and so forth, aren't going to get your blood serum up to the point that you're likely to be too concerned. That's probably not a good way of putting it, but whereas in Europe, if you do end up with a tolerable weekly intake of 4.4 nanograms per kilogram body weight per week, for 4 PFAS combined, then you start to be in the realm where normal exposures from food sources, dust, etc., start to become real issues. So the fact that in Australia it's very much an AFFF story probably is for a couple of those reasons. It's not that we don't care, it's sort of an artefact of where we are in Australia.
Jen?
Yeah, I was just going to say, I agree with Carl there on a lot. It's about what's the, one is the target. And in our case, you know, the target set. I suppose we talk a lot. I mentioned for my colleagues who would be more focused on ecosystems and acknowledge their work, because I do work in human health. I'm probably a little bit more focused myself towards, you know, what are our health-based guideline values, and we've set a target in Australia that, you know, is quite different to maybe, like as Carl says, for what we might see in Europe or elsewhere. That said, I would say we've got very conservative in soil investigation levels, for example. We do think about pathways that aren't necessarily captured by other jurisdictions in sort of their base screening levels. So we do have some quite conservative approaches within it, but it is, we like I said at the beginning of the talk, a lot of our most significant issues in terms of runoff and sort of dealing with the top heavy issues, it has been much more around dealing with AFFF foam's impacts. And then, you know, as we progress, no doubt we will increasingly focus on some of those other more diffuse sources, but it's an even more complex problem then, because you are dealing with a bunch of diffuse sources. So it's not that we don't care, we do care, but at the moment, I think a lot of the priority and heavy work is still in the stage of actually dealing with the impact of AFFF foams.
Just add to that, in Australia, we have a regulatory divide between the Commonwealth and the states, where usually for products and the like, that's Commonwealth. And usually if you have contamination in the environment, that's at the states. And so that also means what you care about depends on who you ask.
Yeah, true.
Yes, there is a regulatory divide, and it becomes very noticeable during COVID times. It's interesting what you're saying, because some of the evidence of health issues, of course, comes from background populations and cholesterol, for example. And the background population is all contaminated, unrelated to AFFF, I would make that claim. So it's interesting that we are a bit laissez-faire on that side. But this session is about remediation. I mean, source control is also a form of remediation, I think, and that's where the regulator has a big role.
Yeah, so I was going to kind of say, it's not to say that we don't care, but and obviously I didn't even talk to the permissioning stream of things within the talk, really focused on our remediation issues associated with contaminated sites. But from a preventative perspective, then, you know, obviously we are thinking a little bit more broadly, and you can certainly see other states looking more broadly. Like I think Queensland tends to definitely expand the number of PFAS that they'd look to, but sure, I probably should stick in my Victorian wheelhouse. But, you know, so I think it's not limited, but when we're talking about remediation of contaminated sites, I guess our starting point is the framework we have. There's the baseline criteria that we've got to start with and move from there. But we'll always look to see what's the additional reduction in total PFAS as well in any kind of remediation. So.
Look, that leads me then on to the question that Robert, maybe you can unmute yourself and ask the question live, and you have your hand up anyway. But in that tunnel digging spoils, that's nothing to do with AFFF. Does it have anything to do with AFFF, or where is the contamination coming from? I'm asking you.
Okay, my question, so that everybody knows, you very carefully skirted around this issue of the Westgate Tunnel spoils, Jennifer. So thanks for your talk, very good talk. Thanks very much. And I'm not trying to press you too hard, but if you're willing to say a few words about that, then I'm very interested to listen.
I guess I'm not too sure exactly what the question is. I suppose, again, I suppose it's a different setting. So maybe for context for others, it's a large infrastructure project that's going to generate a significant amount of spoil, and groundwater is contaminated. So therefore, there is a management measures needed, I suppose, is how to look at it. So I deal with it, in that context. It's very much about a permissioning stream. So that's the main reason why. So is what exactly, I suppose, is the question in relation
no, you were talking about soil, and you were talking, I mean, I'm not in Victoria, but to us, it seems to be the major PFAS issue, and it's certainly the most controversial. Government's overriding its own legislation in order to drive things through, that kind of thing. So it's kind of it looks like a very big thing from the outside, and then transferring large volumes of soil to several communities where there are landfills. So that's really the motivation for the question.
So I suppose I'm not going to comment on some of the sort of some aspects of that.
Yes, sure.
But it's
sure.
That when we have got large infrastructure projects of any nature that generates waste, you're going to have to be able to manage that waste in some way. And so the way pretty much, everything is all on the EPA Victoria website as to how that is managed. But in effect, it is that we do need to be able to address potential risks associated with PFAS that might be in those soils. So for that reason, there is a series of environmental management plans that have been developed for various locations, and they do look to how that will manage the transport, storage and containment of that waste. So in the midst of that, there's a risk, the risks have to be characterized right through the process. So it's not too different to most other waste settings, I would imagine.
I quite understand you probably can't talk too much, and that's understandable. Coming back to Joe Chen's question though, probably the source of PFAS in that soil was AFFF, because it comes from chemical facilities that were on the shore of or close to the water's edge, and there was a major chemical fire in that region 20-30 years ago. So there's some kind of legacy history of use of AFFF, which could have been the reason for those soils to have been contaminated. But I haven't seen enough data to be able to make any further comment on that. There's very little data that's publicly available.
Okay.
You're muted, Joe Chen. Yeah.
No, go on.
Sorry.
Any
done.
question?
Thank you.
Any other questions? Sorry, this is just the normal hiccups when you are not in the same room, or even if you're in the same room. Kids out there, you want to ask questions to the mighty Carl and the superiors Jen? Okay. I don't know who of you mentioned proportional to risk being managed. I think you both actually did in one way or the other. In risk assessment, when I taught it, I was always talking about the receptor. And the receptor is probable. So how are we making that? How are we deciding? I mean, the perception of risk to individuals varies so much. And the real risk we struggle to understand probably still. Do we agree on this?
So the risks have to be managed. And so we have human health guidance values here in Australia, just as there are similar values in various other parts of the world. We can't end up with a situation where there are people who are exposed above those lines in the sand that represent what's safe. So that's not what the proportionate argument is about. It's not saying that, oh, we're going to sort of help most people and leave some people in the lurch. That's not really it. What it may be saying is more, well, there's a limit on how much we can remediate, and so therefore we may need to institute some other controls in order to make sure that those receptors, those people, are safe. And it may be that if you take a proportionate response, that you may be pushing more towards some of those other controls and away from direct remediation in order to address those risks. Whereas if you don't take a proportionate response, if it's a purely risk-based response, it would be, well, spend as much money as you've got to, and don't worry about the other environmental consequences and so on and so forth. You simply have to get to the point of using remediation to get to those risks. So I think that's kind of, where this proportionality comes in. Now, of course, different people have a different opinion on what that proportionality is. And for folks in the other parts of the world, in Australia, we have a system in many of our states where, not for PFAS specifically, but just for contaminated land, we have a system where people can be accredited by EPAs as auditors, as environmental auditors. And so what they allow is for both investigations and remediations, they are an effective third party, if you like, that can help give assurance to communities and to regulators, etc., that this polluter that is paying to fix the problem has actually done enough or has done as much as they possibly can. So that's one strategy that we have in Australia that we can use to help make sure that this concept of proportionality has been achieved.
Yeah, I'd even add to that, Carl, and say in some states those auditors are this legal liabilities that really, they are truly independent. So it's a relatively robust setup in that sense.
Yeah, it is a bit complicated by the fact in Australia, and maybe similar situations in other parts of the world, where you can have large polluting bodies. So in Australia, so defence, or a large Commonwealth-run airport, where the airport or the defence base is on Commonwealth land, federal land, but the regulators are on state land outside those airports or bases, etc. And then that structure gets a little bit strained. In Australia, Defence is doing what it can to work in concert with the state regulators. But that's, at the end of the day, it's their choice to do so. Not, every organisation may not necessarily take a similar approach. There was a very, very interesting case in Japan in the media recently of a US military base in Japan and friction caused by release of PFOS contaminated water or wastewater. And so, that brings into account international jurisdictional issues, which in Australia we're a sea-locked country by ourselves. At least we don't have those complications.
There is a question from Nathan. So Nathan, how about you show yourself and ask that question directly?
Sure. My question is in July or August, the US Congress put forward the PFAS Action Act of 2021, which is going to looking at major controlling on the US, the PFAS. How do you think this implications for Australia? Because Australia is a little bit notorious for following what the US does. So what do you think the implications of that will be?
Jen, you first.
I think this is where you would probably need somebody from Commonwealth actually who'd probably best off to respond to that. But I can only see from our perspective, from an Australian perspective, that we can follow our existing frameworks, that being what was NICS, NAS is now ACEs, whatnot. through our own regulatory framework. I don't know that we'd see significant impact to the Australian approach anytime in the near future. But then again, could be completely wrong, you know. So I don't know, Carl, you've got thoughts there?
Yeah, in our contaminated sphere, we do sometimes pick things up from US. That's certainly true. So examples like our Australian standard leach procedure is adapted from the US EPA TCLP. So you do get those examples, but where we have things already in place, we tend not to lean on other things, and things around us can change like crazy. But if we've already got things in place, then we don't necessarily go looking beyond those. The NDAA, so Nathan, can you give some specific examples of what in there you think might influence Australia? That might be easier for us to answer.
Well, it's complicated because obviously in Congress, and obviously we'll go under multiple changes before it even hits the Senate. But the critical ones was that they're starting to actually looking at fully restricting all the PFAS chains, including the short ones. Australia's only just in March just banned in New South Wales just banned the long chain PFAS usage in firefighting foams for actual fighting fires. So in that circumstance, the US seems to be a little bit trying to go for a federal banning of it. Obviously, the correct comment about obviously we can't comment on what the Commonwealth might do versus what the states might do. It's a bit complicated, but I think it'd be interesting to see how the Australia goes towards banning all the chains. And also in the bill as well was conversations about actual directions of remediation, what's the best technologies to use, what's the limits, how much PFAS can we release into the environment by remediation technologies. There's a lot of interesting facts in it. It'll be interesting to see how it goes in the US, but it'd be also interesting to see how Australia implicates or brings up something similar federally or even per state, because each state has a different opinion on how PFAS goes, and it seems like at every step there's a delay between federal states, as we all know. But yeah, it'd be interesting to see how sorry, go on.
So Queensland actually has in their environmental legislation considered PFAS other than the big three. So the big three for the rest of Australia, PFOS, PFOA and hexane sulfonate. Queensland has included all PFAS as prescribed contaminants for the purpose of releasing water to environmental systems. And they've also included PFAS more generally in various other things, such as looking at their biosolids, waste classification, and so on and so forth. So they've done that. And when I've talked to a few regulators from other states, and Jen can answer in a moment, maybe for Victoria or may not, but certainly when I've sort of talked behind the scenes to a couple of state regulators, the answer has been very clearly they didn't feel quite ready and wanting to talk about it, and it's a conversation they really want to have through the National Chemicals Working Group, which is the body that produces the Australian PFAS National Environmental Management Plan. And so rather than run off and come up with a whole bunch of different ways of addressing that problem of which PFAS to include, but what I might do is just loop back to the question that Jochen asked earlier on, right at the beginning, about, is this just an AFFF issue? And so if my answer kind of holds that yes, in Australia, because of that route to environment, and we don't have those manufacturing centres and so on and so forth, and the other answers I gave, then if it is an AFFF issue, then you expect to see PFOS and hexane sulfonate and some other things from the fluorotelmer foams. But what we actually tend to see is that that's actually true. We see a lot of sites that are dominated by PFOS and hexane sulfonate signatures, which I think Jen also made note of. And so if we remediate to take care of those, we're by default remediating to take care of everything else. I think, yeah, there's not necessarily the same driver for us to jump on what's being done overseas, such as the US, because they have different drivers. The other one is for them, drinking water is so important, PFAS in drinking water, and same in parts of Europe where groundwater is used so much. or there are large river systems that have been impacted by industry, etc. We don't tend to have that same situation. We're not seeing many situations at all where you see large drinking water sources contaminated by PFAS in Australia. So for us here, again, probably not the same driver to just go, somebody else has done something, therefore we'll do that.
Yeah, good points. Quick follow-up question. When you say Queensland has a complete ban on PFAS, that's a extended family chain, and there is some helpful PFAS within that family chain. Is that a complete white ban, or is that a ban on just the firefighting family, the AFFF families?
So no, I didn't say a ban. So they have listed all PFAS as prescribed contaminants for the purpose of releasing water to the environment. So it's a case of if you have wastewater or water and you've treated it and it's still got PFAS in it, and you dump that, you release that to environment, then unless you have specific approval for that, then that's not acceptable under the Act. So the closest you get to a ban is the firefighting foam policies, which again, they can't. It's hard for a state to come out and ban things and products because that's not their realm. But what they can do is they can restrict you from using those products, which is essentially, I guess, what they've probably done in Queensland and South Australia, whatever. So, but those of in Queensland and New South Wales are very tied to long chain PFAS, so they have a definition that is loosely tied to the OECD definition for long chain PFAS. South Australia, they haven't put in a definition. It makes it a bit harder to work out what's acceptable, what's not. It's in Australia. The approach from the Commonwealth so far has been, it seems, more to work with industry rather than place bans. And so Commonwealth Department of Agriculture, Water and Environment is working, for example, I believe with textile industries, the people who produce carpets, etc., to make sure that they understand where they're using PFAS and find ways to stop using those. So more a voluntary approach, I believe.
Yeah, thanks for that.
Let me ask a bit more concrete question. While there is a lack of enthusiastic other PhD students who ask questions here, I think they are eating too many chocolates in those conference rooms here. I just came in there, it sounds like a party. Let's quickly talk a little bit about sorber materials. Carl, you were quite enthusiastic, and Jen also, showing sorber materials do the job. We also work with sorber materials, although at concentrations that are super high. And there was even a question about using biochar as a sorbent. What's the social acceptability? This is a little bit provocative, but what's the social acceptability to say, we actually leave the PFAS there, we just slow it down moving offsite? I mean, that's what sorber materials do. They just make it extremely slow offsite transport. Is that right? Do you see it the same way? So slow that we practically don't notice anymore.
I'm very happy to answer that, but I've also been hogging things a bit. So Jen, if you want to step in.
Sorry, trying to find my mute button there. Interesting, social acceptability. I think from our experience so far, it's the, and I'm sure there's plenty who will maybe argue against me or whatever, but I tend to see that people are interested in the outcome. They want to know, has risk been reduced? And when we're dealing with, often we're seeing a mobilization on site, and if it's aiming and looking at reducing or what's moving off site, that's really part of the narrative that people are interested in hearing and understanding. That said, we do see a lot of on-site encapsulation, I'm going to be honest. So I think Carl's probably had, by the nature of his role, exposure to a lot of different approaches that we're not necessarily always seeing coming through our permissioning streams or whatnot. So I'd be interested in his thoughts and experiences on a project level. But from my experience, most people just want to know, how are you going to resolve this impact to me, and how does this reach the outcome? Maybe a little bit less. So they'll typically have concerns around, well, will that, how long will that last for? What if you have, an unexpected event that might suddenly change the risk profile? But we can usually start to kind of step through those pieces as part of that risk mitigation measures, or talk through validation measures, contingency, and whatnot, to address those kind of queries and concerns.
When you have large sites and they've had PFAS impacts for a long period of time, then in pretty much most cases, you're going to have a large area of groundwater off-site that is impacted. And that genie is out of that bottle and it's not going back in. And this is one of the really difficult things you've got to do, is to try and message to people to say, sorry, we cannot clean up that aquifer. And it would be the same if it was chlorinated solvents. It's not just PFAS. If you've got any kind of persistent contaminant that's not going to break down itself out there in any reasonable amount of time, once you have that large contaminated aquifer, then you've got difficulties. And so then you are in the realm of, what can we do? And one of the things we can do is we can stop more PFAS coming off our contaminated sites, whoever is the owner of that contaminated site. Now, if it's a large site like an airport or a defence base.
We're not stopping it completely, Carl. We are just slowing it down. Do we agree on that?
We are slowing it down to a massive rate, and that is really, really important. Yeah, correct. You're not completely stopping it, but you are certainly buying yourself time, and you are buying yourself time in a way that is environmentally and economically more sustainable than other solutions. So you can pay a hell of a lot more money to do other things, and you won't have actually achieved anything more in terms of actually addressing the risks. So it's particularly focused around where you have very large amounts of soil with low concentrations of PFAS, which we are learning, even though they're low concentrations, they're still contributing significant flux of PFAS off-site via surface water. So something's got to be done about them. But digging up all of the soil at a very large installation and getting rid of all of that soil is not environmentally sustainable, it's not economically sustainable. And so soil stabilisation provides something in the toolbox to just, slow it down, stop that PFAS from going off-site. And, you never know, maybe there will be more economical solutions for soil more generally in the future. In the meantime, it's for those large areas of low concentration soils, I haven't seen too much else that's going to compete.
All these immobilization methods or sorbent materials, they also, well, in my experience, they also bind phosphate quite substantially. And have you seen, are you doing something then to still allow plants to grow, that they still have enough phosphate and other things that are potentially bound?
Yeah, so Defence is getting CSIRO to do some research where they're looking at bioaccumulation and those kinds of effects. And part of that is very much to ask the question, not just what's happening with PFAS, but can the plants grow, can the worms get on happily, etc. And we don't have published results yet, but initially, certainly there is indication that what you say is exactly what happens. You lock up nutrients. Now you can chuck in extra nutrients if you want, but that's not the best outcome. But so the case study that I showed, the amended soil was put down, then there was sand placed on top of that, and then turfing on top of that. So the idea being that you know, you're not expecting that soil at the moment to be a fully functioning soil. You're going to turf on top of it.
Good. Are there any other questions?
Robert has his hand up.
Oh, sorry, Robert.
Sorry, there we are. Yeah, I'm just following on that question and a bit of a sachet back. So if you're planning to move, just as an example, 3 million tonnes of spoil from an infrastructure project and put that in a local community in Victoria, could you do some kind of preventative sorption treatment? Because what might come to light in 5 or 10 years' time is you might find that there's all these short chains present, or you might find that there's other things that could have happened in interaction of that soil. So why not do things now in order to minimize future risks rather than create one problem from another problem? So instead of just moving it somewhere and pushing it onto a different community where potentially it could even have a greater risk than where it is now, could we actually use these technologies now and do something with it?
Now,
go, Jen. Question there, Carl. I got to just
sorry, Jen.
It might be worthwhile going to check out the EPA Victoria website and the environmental management plans that are on that web page.
They're heavily redacted, Jennifer. So they're heavily redacted, and there's not enough information for someone like myself to make any judgment at all on those reports. So that's the problem.
What I would say is that they're not so redacted as that there's an assumption that there's no what the management measures that will be in place are there. I don't really want to kind of focus in on this one particular product, because I don't think it's the purpose of this actual session, I'm going to be honest. But you know, there's certainly going to be lots of different factors for us in relation to something like the immobilization, as Carl is talking about it as a regulator. We just want to know, will it be effective? So a lot of that is going to be taking in understanding, understanding, is that technology effective? So, some of the studies and research and whatnot that is going on are going to help facilitate that. Sometimes we might have things like pilot trials as well. We'll also look to have significant validation and monitoring programs in place post installation to understand, is it actually working? And then from that contingency plan, so that if it isn't for some reason, that something can be done about it. So it's not just sort of willy-nilly sort of thrown in a corner there with no subsequent ongoing considerations.
Just adding to that, EPAs have remediation hierarchies and waste hierarchies where they prioritize, and in fact, I think Jen brought one up in her talk, where they prioritise on-site solutions. The last thing you want to do is to dig everything up and send away to a hole in the ground, or a thermal facility, etc., whatever. So those hierarchies exist, and if there are consultants who are doing the remediation options assessments, etc., they should be thinking about those hierarchies as they're doing it and trying to look for more sustainable solutions, which could include soil stabilisation.
I have a hand up from the PhD students or one of the postdoc rooms at QUAIS. Okay, who is the keen one?
I have a follow-up question. I mean, similar to what Jochen asked about adsorbents as a medium to immobilize PFAS. Now, I would like to know if any company or organization are looking at installing permeable barriers around the site which are contaminated with PFAS. So rather than trying to absorb PFAS, just divert the aquifer. I mean, isolate the aquifer where the PFAS is, and then divert the upstream aquifer to a different direction. And if there's no water or aquifer moving through that section, that kind of
so a form of
immobilizes the PFAS straight there.
Yes. Yeah. That's a form of hydraulic containment, and it has been tried. I've not seen a whole lot of data for it. I mean, obviously, you know, one of the things you're going to do to try that is pump cement down, and cement will absorb a certain amount of the PFAS itself. But I guess that you know, that may be an approach that maybe is, you know, possibly going to be tried at a small site. And so, you know, maybe something on the scale of a small fire station, you know, something like that. When you've got a commercial airport or a defence base and you've got 7 or 12 source areas and they're spread out over a long front, and then you've, you know, so all of the plumes from those will merge together, and you'll essentially have a plume front of, you know, whatever it is, 200 metres, 300 metres or so. If you're going to try and block that amount of groundwater, then you'll also potentially run into serious issues of where the water goes, and so on and so forth. So I think the scale for a large site defeats that.
Carl, that's a great one. Yes, I would actually have loved Lutz to help answer this, because I think he's been working in this space, and I think they've done some of that stuff in Europe. For example, at Düsseldorf Airport, I've seen some slides in, I say Düsseldorf purposely with the Australian accent. But when you gave your talk and you mentioned what's done in Oki, Carl, so you're pumping water out of the ground to be treated with these two techniques, the ETC2 and Evocra, or whatever it's called, the OPEC. Where does the water come from that you're pumping out of the ground? And does that pull water in somewhere? I'm just, can I say that I've learned in my experience with PFAS, I learned a lot about hydrology and how complex and how incredibly, almost incomprehensible hydrology is. So where does that water come from, Carl, in Oki?
So one of them's at a former fire training area, one of them is at a current fire training area. There's aquifer, so the aquifer below in Oki is a very tight clay. So for the most part, the groundwater is moving extremely slowly underneath, and where it's moving extremely slowly, then you can get high concentrations because PFAS has been used a lot and then it's not gone anywhere in a great hurry. So you can, by pumping and treating, get a fair bit of that mass back out of the ground if that's your remedial objective. There are specific areas of higher conductivity where the water's flowing a bit faster. And of course, it's under the ground, so you don't necessarily know exactly where those are. But yeah, so essentially the water, it is just the regional aquifer that's underneath the base.
So it comes from upstream from the side, and it sort of travels through the side slowly, and you're sucking clean water through the side. And by doing so, you are cleaning up the side a little bit.
So yeah, in the case of the ECT2 one, for example, so they're drawing from the aquifer, they're cleaning it up to the, you know, to a very good standard, and they're pumping it back down into the aquifer. And you know, they've made things far better than it was before it came. Often with these sites, there's more than one aquifer. So depending on how deep you go, you can have multiple aquifers, one of which may be contaminated with PFAS, another one may not be contaminated with PFAS. You've got to be careful that you don't do things that create connectivity between aquifers and cause a previously uncontaminated one to become contaminated as part of either your investigation efforts or your remediation efforts. So there are plenty of complications in terms of trying to deal with hydrogeology.
I think we are slowly wrapping up before we have a few poster presentations. I have one important question to wrap up later, mostly for Chen, but before that, Andressa, do you want to show your face and ask your question with your very nice South American accent?
Hi, I'm a bit shy. Can you see my face?
Yes.
Thank you for all discussions being very helpful. I'm very interested about the sources of PFAS because it's part of my study. And regarding this, I understood that the requirements now is more voluntary for the industry than harder than requirement. But is there any type of requirement that the industry that consumes products with PFAS in their content, that they have to analyze their wastewater before they dump it into the sewage? Or I don't know, it's the company just does it voluntarily?
Are there trade waste limits?
Yeah, other trade. Jen, do you want me to have first go? Trade waste agreements are specific between the company and the water treatment operator. So that'll either be a water utility or a council. Just depends on who's operating the sewage treatment plant, the wastewater treatment plant. And so the trade waste agreement would typically include, for example, hydrocarbons, metals, ammonia, those sorts of things. Whether or not they include PFAS is a really, really interesting question. And so if you are in an area where there has been an active PFAS investigation, so near one of the big defence bases where there's been, etc., it's quite likely that there's already enough attention on the matter that the water utility would have gone to their customers and said, right, we're going to put PFAS limits on your trade waste. In other areas where it hasn't received that kind of attention yet, you'll find many situations where there would be nothing in the trade waste agreement at the moment for PFAS. So there's no blanket answer to that. It depends where you are. As the EPAs get more ramped up in terms of pushing the STPs, the sewage treatment plants, in terms of their effluents, then they will look and turn upstream to where PFAS is coming into their water treatment plant. So then they will start putting pressure on trade waste agreements, etc., whatever. So we're in this position in Australia with that at the moment where, sort of seeing where it's going a little bit in most situations. I'm not sure if Jen has a...
Yeah, I think the only thing I'd add to that, Carl, is I think, like you say, certain areas there will have been more greater attention or need or whatnot. So certain water authorities will be looking, will be wanting to know what is their intake. So it is going to be on a case-by-case basis, I guess. And yeah, so worth contacting if it's what your project is about to explore how are they looking at their sources coming in, because they've got a lot of different issues to try and understand about what the source intake is.
By the way, Andressa, there is a Canadian paper, poster presentation, that is about sources of PFAS in wastewater on the WUFA website or as a poster. And it discusses what the type of sources are. So I thought of you when I saw that. Andressa is doing a PhD on sources of PFAS in wastewater. Good to know.
It's a really, really important issue because if, for example, a lot of PFAS is coming from domestic sources, then that means putting in trade waste controls will have limited impact in terms of the overall control. And that pushes the interest back upstream to the Commonwealth government in terms of product control. So it's a great question. We need it answered. So look forward to your work.
Oh, great. I was worried because you told about the main source would be the 3F. And yeah, my study is just to look forward to try to identify residential and potential industrial sources. I didn't know how relevant it would be, but great to know that's relevant. Thank you.
Good. Quay's room. There is a question, hand up from Quay's room.
That's me again. I don't want to open a can of worms here, but a very quick question. We talk a lot about PFAS released from industry, but I don't hear a lot of discussion, and maybe a little bit of murmur about PFAS released from landfill sites. I mean, and that doesn't look like the councils are taking some proactive approaches towards it, but purely voluntarily. There hasn't been any strict regulations coming out that these landfill leachates needs to be managed in certain manner to control PFAS. I mean, does anyone know, is something happening in that area?
Yeah, I'd say
I
so.
assume-
EPA Victoria definitely did. We did some work over the last couple of years around understanding landfill leachate. It's done by a colleague of mine who's now actually no longer with EPA. So I can certainly send on some links to that work. The findings were somewhat relevant to our old legislation, so I'm a bit conscious about that. But ultimately, from the Victorian studies anyway, it wasn't felt that there was a really significant input from a waste perspective from landfill leachate. But I haven't got all of the details of that study right with me right now, so I'll certainly get it and I can send it on.
In fact, Pradeep, I don't know whether you know the work of Christy Gallen from our team, and she did landfill leachates. And again, at least when the landfill leachates were transported to wastewater treatment plants, it seemed to be very little contribution to the overall mass loads of going into the wastewater treatment plants. But of course, all landfills will leak one day, and that's a different story. Okay, I think we are sort of wrapping up the question, but I have one big question that bugs me the most. And that is really the ultimate question in the remediation session. I mean, Carl answered it a little bit, saying that it all works. But I wonder a little bit, what happens if the remediation is unsuccessful for a site and you do not achieve those expected reductions, or they are super slow? What do you do then?
The whole process is so slow anyway. If you think about it from investigation through to remediation, I think one of the things Carl mentioned as well was about you're more often than not have multiple technologies involved in any one site in dealing with different types of issues. It's also going to be staged. So we start often with, especially offsite with administrative controls, that can often be one of the first things that happens. Risk communication is a really important part of it. So it does take a long time to get there. I think the aim, the objective is, in our case anyway, certainly to restore those environmental values. We really want to be proportionate and put those efforts in where they're going to have the biggest impact, because we are often dealing with extensive issues. Not always, sometimes they are quite small localized sites or whatnot. If and where we just, more often than not, we'll end up with some of those sort of more simple, I suppose, approaches, those approaches that might manage the risk for now. So we do have a lot of, let's say, on-site encapsulation, allowing for future, changes down the line if there's, better improvements in technology that will be more successful. But ultimately, we're just going to you just have to keep on trying there, don't you? And
I think my question, Jen, or also Carl, my question is much more about, remediation tries often to capture somewhere near the source, the chemical near the source, or near some rather big source. But a lot of it, and Carl, I remember we had this discussion, a lot of it is already beyond that source and is on its way, and it will take a lot, and it took years to get there. And so remediation is one, and to kept the source, but then to actually prevent exposure on the receiving environment, you have to protect it on the other end.
But we were phrased of on and from the premises. So certainly we do seek remediation of let's say impacted dams on farms, for example, and that's why I talked about why I was trying to talk to having really proportionate risk assessment, because we want to really identify those that need it, not spend effort and energy given the extent of the works that have to occur. You want to make sure that you're focusing in on those areas that will truly need it off-site. If there is an off-site property, for example, where the soils have got a heavy impact and it's a residential setting, we would expect that to be included in the remediation strategy. So it's not limited to just managing on-site source issues, but the very nature of having an ongoing source that's continually contributing is probably the first step in a long process. And then within that, we have, because it'll take so long, various different controls that might need to be put in place while you slowly keep moving forward and progressing the issue. But yeah, ultimately, all environmental values down the line, you aim to remediate them, and that won't be maybe possible for certain water bodies, for example. But we've still seen improvements in fish, so I'd like to be glass half full and say eventually these things will show some broader benefit, not just on the site.
No, Carl, comment. Okay, final question from Carl. You want to throw in your...
Just adding to that, and that all makes an awful lot of sense. Only adding to that is monitoring and having an iterative approach where you feed back your information, you reassess your risks. What do we have to do from here? It's that iterative approach is absolutely key.
I mean, using my right here, I know sort of a case where remediation happened in Sydney Harbour, not for PFAS, but for an even more toxic POM. And I think 20 years later, the results suggested there was actually no change in the concentration of these chemicals in certain species. And arguably that remediation cost an awful lot of money and wasn't very effective. How do we deal with that? Are we revising? Are we getting better? Are we thinking a bit harder what we should be doing? Robert, have you got an answer to that, or do you want to?
I have a parallel question, and this is we didn't know about PFAS 10 years ago, 15 years ago, and there are a lot of contaminated sites, fairly significant contaminated sites like oil refineries, petroleum depots and things that were cleaned up. They have a site audit certificate issued, but there would have been PFAS at those sites. And it's just gone through. They've been officially in the legislative and regulatory framework, they've been cleaned up. These are the things that worry me, because there are probably people living there now and there could be impacts that was never addressed. So these are the sorts of things that I really worry about with emerging contaminants, is that you can undertake an action and you think, I mean, you've done the best that you can given what you knew at the time, but it wasn't good enough. And how do we go back to these sites? How do we revisit these decisions in order to protect the people that are there now?
No, Carl, if you wanted it. There are sites I know that we have revisited for sure. An audit is always point in time. Like that's the purpose of them. So we do have audits, for example, that from the early 90s that didn't even consider groundwater. And then vapor intrusion was never something that was considered. It was never, just wasn't there. Now it's emerging contaminants. But typically what we will find is that particularly in the urban settings, there's just so much turnover, development, or whatnot, that we actually do end up revisiting a lot of sites in different settings. I can think of a couple of PFAS sites that have sites that were exactly that type of setting, where it was pre-PFAS given, an okay, because it wasn't a contaminant of that was even known really at that point, that are subsequently being reassessed. So it does happen, but much like most contaminated land, there's plenty of it out there, that we just have to keep on looking and assessing.
All
in
right.
the National Environmental Management Plan, there's a list of areas or industries that would likely to be associated with PFAS use. And so I'm pretty sure the EPAs have gone around and had a look at where they're likely to find things and be informed by that sort of thing. I don't think they're just taking it all lying down.
Yes, emerging contaminants. A very vague term. By the way, Robert, we did know. Oh, are you still having your hand up, or are you having your hand up?
No,
again?
I'll turn that off. Yeah.
Okay. All right. I think we're gonna fade out with a couple of posters. Who is interested? Those who want to leave, these posters are available also on site, but let's start with Nathan. Nathan's poster on thermal degradation. So we have 4 posters, I think, 4 or 5 posters, and one quick presentation of the Emma of her poster. Okay, let's do this. Let's see whether I can do the share screen. Is it? Mm-hmm. Okay. Share.
Hello, everybody. I'm Nathan. I'm a PhD student from the University of Newcastle. We are presenting a virtual poster on the studies on the influence of the reactive materials film decomposition PFAS at the FLUOROS Global 2021 conference. To help give some context, I thought it might be a good idea to do a quick video and a bit of a presentation on our poster. Jumping over across to our presentation, to begin with, PFAS are known as organic fluorinated compounds. PFAS are quickly becoming the most notorious chemicals in the environment. So if you do a quick search of PFAS on Google and click views, you probably see 2 or 3 articles just from today alone about the newest PFAS contaminated sites. In saying that, if you do more further research, you'll find that PFOS, which is the focus of this poster, is one of the most commonly found PFAS in a contaminated site. Interestingly enough, environmental agencies all throughout the world are starting to look at banning or phasing out the use of long-chain PFAS. But the most notorious one is the PFAS Action Act, which is the US Congress bill which has been put forward to ban out and start considering technologies to remediate PFAS in the environment. So with potential plans all throughout the world to remediate PFAS contaminated sites, probably the most leading technology right now is thermal treatment. As an example, thermal desorption. So I don't have to go through the poster. I will link in the description of the leading Australian technology, which is called SourceZone, in the description of this YouTube video. So how does thermal decomposition PFOS occur? Well, we recently did a study on this. I will link that in the description as well. We know at temperatures above 400 degrees, thermal decomposition PFOS can start occurring. What this means is that this PFOS molecule here will release a HF molecule to form an alpha sulfide. Now, this alpha sulfide will rapidly, I should really rephrase, nearly instantaneously form the perfluoroaldehyde, and perfluoroaldehyde and plus sulfur dioxide. This can be assumed for all perfluorosulfonic acids, not just PFOS. Now, this is called perfluorooctanol fluoride in PFOS. It's a C8 perfluoroaldehyde. In our paper, we also pointed out that there could be evidence of that the reactive materials, such as the aluminum, could actually influence the thermal decomposition PFOS. We need limited knowledge. It needs a bit more further information. So experimental is pretty simple. Just a 3-zone furnace, inert gases with a FTII, micro GC, and GC mass all there to analyze our gas phase analysis. And we are studying 3 reactive materials with poster: quartz, alpha alumina, and stainless steel 316. Starting off with quartz, we know that we saw straight away there was a heterogeneous reaction between PFOS and quartz forming silicon tetrafluoride. This is first noted at temperatures above 550 degrees, but could have be seen lower depending on your residence time.
And there's a major increase in the concentration of silicon tetrafluoride above 700 degrees and even higher 800 degrees. It's got really a lot of concentration of silicon tetrafluoride coming up at these temperatures. The quartz, we know that the potential of the quartz surface could be reacting with HF, which means we see we have less than 10 ppm. While on stainless steel, we have much higher. And same with alpha alumina, we have both have higher amount of concentration HF. So HF is disappearing in this, so it could be potentially forming silicon tetrafluoride. There's also potential that the perfluoroaldehydes as well are reacting directly with the quartz surface. They're also known to react with the quartz surface to form silicon tetrafluoride. So in reality, you really should reconsider using quartz as a reactive material when working with fluorinated chemicals. So jumping over to alpha alumina, starting with the main products, HF, CO2, CO, carbon fluoride, perfluoroaldehydes, perfluoroalkenes, SO2, and the generic fluorocarbon vibration region, which is the C2F4, which is tetrafluoroethylene, which is the main product in alumina, C2F6, C2F6, and C2F8, which are more perfluoroalkenes and alkanes. What's interesting is that the alpha alumina interacts with the surface to form to actually accelerate the reaction, so it's actually be catalytic, and this would increase the overall rate of PFAS. Now, what about stainless steel? Well, stainless steel very similar, lower conversion, obviously, because it doesn't act as catalytic, so similar products. However, what's actually most interesting about this, as temperatures approach the oxidation temperature of stainless steel 316, which is about 100 degrees, we start to see the loss of sulfur. So the sulfur dioxide will start to decrease. So we're starting to see a loss of sulfur. This could be evidence that this sulfur is reacting to form with the stainless steel directly. It's actually another heterogeneous reaction, but at much higher temperatures to form the sulfides. So quartz creates silicon tetrafluoride, while alumina favors the formation of C2F4. Stainless steel, however, at temperature above 700 degrees, has the potential reaction to form sulfides, and sulfides such as metal complex sulfides such as molybdenum blue. Thank you very much. I hope you enjoyed my presentation. By all means, ask me any questions.
How do we get out? I'm still learning how to use these techniques. Sorry, guys. Where's the next? We have to go on the WUFA website, which is here. So, how do I close that? Okay. Close this. Sorry. Only a question of hours. How about we do Roberts?
My name is Robert.
Share screen. By the end of the day, I will be really good with this. All right.
Evan from the University of New South Wales in Canberra, Australia. I'm speaking on behalf of the team from UNSW and Macquarie University, Sydney, Australia. I'm going to talk about PFAS removal from contaminated waters and soils by foam fractionation and gas liquid fluidization. So this work examines two methods for PFAS removal. First of all, foam fractionation, in which a surfactant is absorbed to the surfaces of rising gas bubbles in a water column and removed as a foam. Secondly, gas liquid fluidization, in which a soil is liquefied by flows of water and or gas, enabling the removal of contaminants in soluble form as a foam and by the elutriation of fine particles from the soil. So first of all, foam fractionation. Experiments were conducted using a proprietary bench-scale foam fractionation apparatus with injection of air bubbles and separation of the recovered foam without any other additives. Two waters were examined, a synthetic PFAS water, a spiked with light water concentrate, and secondly, a PFAS contaminated groundwater from a military base in Queensland, Australia. These waters had initial PFAS levels 2.7 to 4.1 micrograms per litre, with some differences in composition between the two waters. The results are shown in figure 1. I'll just zoom in. So as you can see in figure 1, all of the 3 criteria species, PFOA, PFHXS and PFOS, were successfully removed in the duration of the experiment to below Australian drinking water standards. And indeed, all of the other long chain species and several short chains were also removed from both waters. An exception was PFXA, which was not successfully removed. The next method is soil fluidization, in which soil was fluidized in column as shown in figure 2. 2 soils were examined, a 300 micron silica sand, 5% kaolinite, spiked at 3 different concentrations with light water concentrate, and also a PFAS contaminated sandy soil from a military base in New South Wales, Australia. The soils had PFAS concentrations between 2,500 and 8,500 micrograms per kilogram, again with some differences between the 2 soils. 3 types of experiments were conducted: liquid fluidization with an upwards flow of water, gas liquid fluidization with upwards flows of water and gas at 2 different water flow rates, and fixed bed flushing with downwards water flow to simulate infiltration. The results are shown in 2 sets of graphs. Zooming in again. As you can see in figure 3, the top bar chart shows the initial concentrations of 3 batches of sand kaolinite soil and final concentrations from the different methods. As can be seen, the liquid fluidization and gas liquid fluidization all successfully remove PFAS from these soils to below the Australian HIL-B concentration, and in some cases below the Australian HIL-A concentration. The graph below shows normalised concentrations to show the effect of composition. And as you can see, composition is relatively unchanged from the original to the final treated soils. These soils are dominated by PFOS, and that composition is reflected in the final soils. The site soils are shown in figure 4A and B. On the left, the initial concentration followed by the final concentrations from gas liquid fluidization experiments and also fixed bed flushing experiment. In this case, the fluidization method was successful in treating this soil to below the Australian HIL-B concentration. The composition is shown in the normalized PFAS concentrations on the right. What you can see here is that although these soils are dominated by PFOS with some other sulfonates also present, they also contain an appreciable level of fossa, and the proportion of fossa in the residual soil after treatment is great. The results, PFAS concentration in the effluent from 2 of the gas liquid fluidization experiments are shown in figure 5. What you can see here is a decline in concentration with time. This follows an exponential decay relationship, which is consistent with the elutriation of fine particles from the soil. And so to conclude, experiments confirm the suitability of foam fractionation for the treatment of PFAS contaminated waters and fluidization for the treatment of PFAS contaminated soils. This research was funded by the Australian Research Council, and I'd like to thank our industry partner, OPEC Systems Proprietary Limited, and the Australian Department of Defence for supply of materials. Thank you. My name is...
Thanks, Robert. Next one. I just always struggle to...
Robert Niven from the University of New South Wales in Canberra, Australia. I'm speaking on behalf of the team from UNSW and Macquarie University, Sydney, Australia. I'm going to talk about PFAS removal from contaminated waters and soils by foam fractionation and gas liquid.
Yeah, little hiccup, but we got there. And now we have to share screen. What would I do with a salad?
Per and polyfluoroalkyl substances are a class of emerging contaminants that can be found worldwide in our aquatic environment. The reason for their presence is that our conventional wastewater treatment plants are unable to remove these contaminants from the water. Therefore, advanced treatment technologies are needed. I'm using nanofiltration membranes in order to remove PFAS from the water and try to investigate the impact of steady state and operating conditions on the rejection performance. In my study, I've tested 5 different nanofiltration membranes of different molecular weight cutoff and membrane material on their performance to reject 9 target PFAS, including short and long chain compounds at a concentration of 1 microgram per liter. I've investigated steady state and then varied operating conditions, including the permeate flux and cross-flow velocity. My findings show that initially the rejection is high for all the membranes, but then it varies within the first 6 hours of filtration. This indicates that absorption plays a really important role of PFAS towards the membrane as well as to the system. The variation and rejection decline about 24 hours after the start of the filtration, which indicates that then at this point the steady state is reached. Furthermore, comparing the different membranes, it shows that the highest rejection was achieved with the membranes of the smallest molecular weight cutoff, which in this case was the NF270 and TS40 membrane. The lowest rejection was shown for the XN45, which has a molecular weight cutoff of 500 Daltons. This comparison shows the importance of size exclusion as a separation mechanism in nanofiltration. Surprisingly, the hydrochlor 10 with a molecular weight cutoff of 3000 Dalton shows surprisingly high rejections, which might be due to the membrane material for this membrane, which is made from polyether sulfone. Following the steady state investigation, I've taken the highest performing membranes, NF270 and TS40, and tested operating conditions. First, varying the permeate flux in a range of 30 to 60 LMH for TS40 and 45 to 90 LMH for NF270. The different range is due to the different permeability of each membrane. The findings results show that varying the permeate flux did not negatively impact PFAS rejection. As another operating condition, I have tested different cross-flow velocities and varied the cross-flow velocity between 0.05 to 0.15 meter per second. And my results show that the PFAS rejection is not significantly impacted when the cross-flow velocity is varied. Overall, my study showed that it is important to establish steady state first in order to take the absorption capacity of PFAS into account and avoid overestimation. But also the importance of size exclusion when the highest rejection was reached for the membranes with the smallest molecular weight cutoff. But most importantly, nanofiltration can successfully be operated with removal higher than 85% at a wide range of permeate flux and cross-flow velocities without having a negative impact on PFAS rejection performance.
Well, and this was from our poster girl, Natasha. And you can see the poster online, of course. So it wasn't my fault. So now I have to get out of there again. No. Sorry.
Per and polyfluoroalkyl substances are a class of emerging.
Escape button is really great, hey?
Hello, everyone. I'm Elisa, a PhD candidate from the
Screen.
University of Queensland, Australia. Hello everyone, I'm Aliza, a PhD candidate from the University of Queensland, Australia. Here I will report my work, which is about evaluating the removal of current polyfluoroalkyl substances using biosorbent. So there are many PFAS removal studies available, but most focus on the removal in ground or surface waters only. However, municipal wastewater treatment plants are also one of the major point sources of PFAS. The poor capture of PFAS of less than 15% at the wastewater treatment plants threaten the long-term health and safety of environmental species and human health. Thus, my study aims to evaluate the removal of 10 targeted PFAS in wastewater using industry-used and emerging sorbents. So here is my experimental flowchart, where all of the sorbents will undergo a 24-hour batch absorption test. The best performing sorbents will then be investigated for their PFAS sorption kinetics, sorption isotherm, determine the effect of natural organic matter, and the sorption using municipal wastewater. So this figure shows the PFAS removal efficiencies of the sorbent study. Results show that activated carbon, anion exchange resin, and beta-cyclodextrin-based polymer are the best performing sorbents, showing 80 to 99% removal of the 10 targeted PFAS. Mineral sorbents, such as zeolite and graphite, have a preferential sorption towards long-chain PFAS only. The reduced graphene oxide, and magnetite nanoparticles have lower PFAS removal due to their surface charge. One of the factors controlling the fate and transport of chemicals in the environment is our phase partitioning behavior. The high solid liquid distribution coefficient, or KD value, of PFAS on the best performing materials show that these chemicals will more likely partition on the sorbent rather than in the clay space, and the opposite is true for lower KD values. The sorption kinetics of these sorbents were investigated to determine the rate of sorption. It shows that activated carbon and beta-cyclodextrin-based polymer have a similar trend, and equilibrium was reached after 4 hours, while anion exchange resin has a lower kinetics and the equilibrium time is reached after 8 hours. This may be attributed to the difference in the particle size, where an ion exchange resin has a bigger particle size. It shows that the particle size of the sorbent is an important parameter for design considerations. The isotherm layer were plotted in both Lemire and Friedrich models. The maximum sorption capacities were calculated, and it shows that PFOS has greater affinity on activated carbon, PFOA on beta-cyclodextrin-based polymer, and PFBA on an ion exchange resin. This information can help in the decision-making on whether to use combined sorbents for maximum PFAS removal or removing targeted PFAS. Lastly, the effect of NOM was investigated, and from this figure, it shows that the presence of natural organic matter decreased the PFAS removal efficiencies of the 3 sorbents in a 4-hour sorption test, indicating a competitive sorption between PFAS and NOM. So, in summary, this study reports the PFAS removal efficiencies of the different sorbents. The takeaway messages are activated carbon, anion exchange resin, and beta-cyclodextrin-based polymer were the best performing sorbents. Chain-length dependent sorption was observed, and negatively charged sorbents had lower PFAS removal. Particle size affects the sorption kinetics. Maximum sorption capacities were also investigated. The presence of natural organic matter negatively affects the PFAS removal efficiencies. And lastly, the sorption experiments on wastewater samples are currently ongoing. Thank you.
Thank you very much.
Hello, everyone. I'm Aliza, a PhD candidate.
Yep. And our last one. And do I now hand over to you, Emma, and you do it from there? Okay, then the key thing is that I mute myself. So our last one will be Emma, and she will be sharing her screen.
Hi everyone, my name is Emma Knight. I am a postdoctoral research fellow at the Queensland Alliance for Environmental Health Sciences under Yokin at the University of Queensland. And the project that we're working on at the moment is the remediation of PFAS contaminated soils using a soil washing treatment train. And this is quite a large project, so I've tried to represent most aspects that we're working on currently. And just in case you can't see, I will zoom in a little bit if I can. Nope, that's the wrong way. So if you're not familiar, soil washing is a contaminant separation technology designed to decrease the amount of contaminated material that needs to be taken off-site, making it a pre-treatment and to subsequent final remediation techniques, including immobilization and incineration. And during soil washing, contaminated soil particles are separated according to size, density, and they're also treated with non-hazardous solvents that dissolve contaminants from the soil. Venture, our industry partner, has pioneered this approach for remediation of PFAS contaminated soils. And the project overall aims to develop soil-specific washing techniques for the treatment of PFAS contaminated soils, which will form the basis for high throughput, cost-effective, routine, and long-term sustainable remediation of PFAS contaminated sites. So the little diagram that we have just here, this shows, I guess, an overview of the project and its 5 work packages. So work package 1 is the characterization of the contaminated soil. So we're looking at soil properties as well as the PFAS profile. These are from AFFF or aqueous film forming foam sites that have been highly contaminated. And then it goes through the soil washing treatment plant, where we then look at work packages 2 and 3, which look at the sorption and desorption of PFAS from the soil and the effectiveness of that. And then we get into work package 4, which will treat any immobilized residual soil fractions. We haven't had too many of those because the process has been quite successful so far. And then work package 5, where we look at how the treated soil can be reused and if there's any transformation of precursors or further transformation of other PFAS in the soil after washing. So I'll give you a quick overview, I guess, of all the 5 work packages we've got. Some we have more work on to date than others. And this is just like a brief overview of all the, quite a few of the aspects that we've looked at so far. So work package 1 is the characterization of a range of contaminated soils for their soil properties and their PFAS concentrations. So here we've just presented 2 highly contaminated Australian AFFF impacted soils, and the soil properties for these range for OC is 0.3 to 1.69, and the clay content also varies quite a lot as well. And there's some other ones, and you can have a look at them on the website later if you're interested. And then we also looked at the concentrations of 28 targeted PFASs, including some PFAA precursors in untreated AFFF soils. And these, we looked at, both targeted, which were presented here, and the non-targeted analysis, which we're still working through. And in the little table, I'm not sure how clear that is for you guys, but the 2 soils vary in concentrations for a number of PFAS, but I guess the 2 standout ones are the concentrations of PFAS and the hexane sulfonate. They're quite a lot higher than the others, and this is quite common for AFFF soils, AFFF impacted soils. So then we scroll back up to the top. So now we're looking at work package 2, where we investigated the sorption and desorption behavior of PFAS in Australian soils. So this first study was actually conducted by one of our PhD students, Rose, at Quays. And she looked at batch equilibrium study, including 10 Australian soils with a range of soil properties, and also 7 targeted PFAS classes. So her 10 soils ranged in various soil properties. And then the batch equilibrium study, where we looked at the log KD, so the soil water partitioning coefficient. And these varied by 1 log among soils, but up to 3 logs among PFAS. So this indicates there's a higher variance when we look at PFAS structural changes when the carbon chain length goes up. But then we see not as much of a difference between soils, potentially meaning that soils have less impact on absorption than the different PFAS. We also then saw log KD values were significantly linearly linked to molecular weight. So these longer chain PFASs that have greater than 350 grams per mole in their molecular weight had R squared of 0.94. So that's quite high, with p-value being quite significant. Log KD values of the PFASs increased when solution pH decreased from 8 to 3 pH units. And the shorter chain PFASs were less affected by these solution changes than the longer chain PFAS. And yeah, as I hinted at before, multiple soil properties describe sorption better than any single soil property. So when we looked at the modeling for sorption of PFAS, what we found was that, no single soil property influences the sorption, which is unusual because for many other contaminants, we look at organic carbon content as a main driver for sorption. So for this second part of WAC Package 2, this was conducted by one of our collaborators at the University of Adelaide, Shervin Kabiri, and she looked at 12 AFFF contaminated soils for PFAS desorption using the Australian Standard Leaching Procedure, or the ASLP. Now, she actually looked at a number of different leaching standards, but we're just presenting the ASLP here. Soils depended on the chemical structure of the compound, so the chain length, as well as the functional head group. And that's what we can see in this figure 3. And desorption of the short chain PFASs were not as affected by changing leachate chemistry. And we also saw this with the batch equilibrium study. The dominant factor affecting PFAS desorption from the soil was the chemical structure rather than the soil properties. Moving on, we get to work package 3. So this one we're looking at the factors that influence the treatment performance of the soil washing treatment plant. So in figure 4, which is this figure here, we see a picture of the soil washing treatment plant in action. And so far, field trials have shown that soil washing works even for soils with high clays. And this is quite unusual because for other soil washing treatment plants that have been applied to different organic contaminants, this has not been as effective for clayey soils. There's also so far been more than 1,100 tons of AFFF contaminated soil. That includes both clay soils and sandy soils. And I think to add to that, there's also been some concrete washed. Wash water is recycled within the plant, so there's limited water loss to the surrounding environment, which means there's less remediation to do in the future as well. So just as an example of the soil washing treatment plant so far, if we look at 2,500 tons of AFFF contaminated clay soil has been remediated through the soil washing treatment plant at roughly 100 tons per day. And this was then done in 25 batches. And removal efficiencies were up to 98% for some of the PFCAs and 99% for some of the PFSAs. And no precursors were really present in this soil as a historical AFFF impacted soil. So if there was any PFAS precursors, this probably has already been transformed if that's the case. And we can see in the box plot here, the mean treated and untreated soils and their PFAS concentrations. And residual PFAS concentrations remained mostly in the fine fractions of the soil. So the soil washing treatment plant breaks up the fractions of the soil to like a gravel, sands, silts, clays, and organics. Sorry, the clays and silts would be together. And no breakthrough of the absorption media during the 250 tons of clay soil. So the media that washes the wash water, there was no breakthrough in that. Now, in work package 4, this is still ongoing as well. We haven't had a lot of fine fractions that have needed to be treated. So we've started preliminary studies to reduce potential leaching of PFAS in soils after washing, but yeah, we haven't had much of that yet. And then we're also in the process of looking at biotic and abiotic transformation of some of the novel AFFF related zwitterionic PFASs. And this is just a figure of the setup. Again, this is by one of our students here, Rose. And so just to wrap up, there are many factors that influence the effect of soil washing remediation processes from the AFFF contaminated soils. And it seems that PFAS chemical structure has a greater effect on sorption and desorption than any specific soil properties. And leaching of the shorter chain compounds was found to be less affected by changing solution chemistry than longer chain PFASs. And leaching of PFASs from soils was significantly reduced by soil washing. So this is a promising novel technology for the remediation of AFFF impacted soils. And we have one paper published already, and there are 2 in progress. Thank you very much.
Okay. Well, and that brings us to the end of this remediation session. Just in time for Lutz joining us. Hi, Lutz. Good morning. I can't hear you yet. Early in the morning. Sorry, Lutz, there must have been some kind of miscommunication between organizers. Don't blame me. So everybody, have a great evening. Lutz, you have a super great morning in Sweden. Maybe we can catch up quickly afterwards and I summarize for you. And all the Queensland folks, we go out to a restaurant. Here is Lutz. Hi, Lutz.
Hi.
You had a good sleep?
Yeah. I think I thought it was a US time, but apparently not.
No, I'm sorry. I don't know how that got lost in translation. Maybe we should have spoken German with each other.
Yes.
All right, everybody. Have a wonderful evening. Jen and Carl and Lutz, thank you so much for your wonderful presentations. Really wonderful. Actually, my introduction was really lousy to you, but
I guess that is the end. Thank you so much. I know this is a bit tough to watch just a full recorded, but I still like the session as it was. I wish Lutz had been there in person, but I think we might have him live in just 20 minutes. So thank you so much for staying here. Tomorrow is going to be more engaging. We have only live sessions. Just a quick word, the 4 o'clock is the poster session in Europe. So we're not going to stream it live here. If you want to get up early, feel free. It will be recorded, it will be in Hoover. But the real program really starts from 8 what's on is check-in and breakfast, and at 8:45 we go over to Brussels. They have a live session through 12:30. We have a quick break, and then we have a live session here through the afternoon. Then we still have time again for posters. So at this point, we have a 15-20 minute break. There's some snacks, and the bar is up in the little room where all the food is served. Thank you for hanging in. hopefully there's time a little bit of posters again or discussion, and there's no food tonight other than what's in the back. And then hopefully see you tomorrow morning at 8ish. Thank you very much.